Hello and welcome to this lecture. So I'm going to show you some quick examples of problems where you can use this kind of algebra. So here is an algebra problem which we used earlier when we did some dynamical systems type example. So let's quickly go through that. So you have a vector y here, and the question asks you to express it in terms of the vector u. And here are the relationships given: ax plus bu is 0, and y is cx plus du. Okay, and x and y and a and b and c and d, all of these guys are suitably defined matrices. And how do you deal with this? So here is a simple little example of how to do this. So you have ax plus bu equals 0, and a is invertible, right? So you can multiply throughout by a inverse, so you're going to get x. In fact, you can write it as ax equals minus bu. Okay, take this to that side and then multiply throughout by a inverse. So you're going to get minus a inverse bu. Okay, so that's easy enough. And then y was cx plus du. Okay, and then you plug in this here. Okay, so if you do that, you're going to get c times minus a inverse bu plus du. So notice how I'm manipulating matrices pretty much like variables in an algebraic equation. So you don't need to do anything special here. So you can do take things common out, but except keep this commutative aspect very carefully in mind. You should not write bu is the same as ub and all. I mean, that doesn't make any sense, right? So you'll be very careful here. Here you can pull u out. So you get here minus c a inverse b. Notice the ordering. I don't change the ordering. That's very important. You can't change the ordering when you multiply matrices, and you get this. So very quickly you're able to just manipulate those equations and get y in terms of u. Okay, so I hope to see this. So this gives you some good example. Okay, look at this one. What's going on here? So it says show that I plus uv whole inverse. So we'll assume I plus a suitable matrix is uv. So I plus uv has to be invertible for this to make sense. Okay, I plus uv whole inverse multiplied by u, it says has to be the same as u multiplied by I plus bu whole inverse. So notice a lot of things people will go wrong here. See, remember uv is not the same as bu. So don't think that this is identically true that way. You have to be very careful here. These are matrices, right? But this ends up being true even if it is not commutative. Okay, so why is that? So maybe I don't need to write it. I'll ask you to imagine. Okay, so you've got I plus uv inverse here. So maybe I'll write this. Okay, it's better to write, I think, right? So let's look at that very quickly. So it says to prove is what? So I plus uv inverse times u is the same as u times I plus vu inverse. So a lot of people start cancelling. You can't do all that. So you can't multiply by u inverse. If you multiply by u inverse, so you don't even know if it's invertible, right? So or maybe I don't know. So it is very complicated to figure out what to do here. So the best thing to do is, if this is true, if you multiply both sides by I plus uv, because I plus uv is an invertible matrix. So if something is true, you can multiply by an invertible matrix, it still has to be true. Okay, if it's not invertible, then it doesn't go both ways. Okay, so this is if and only if same as multiply both sides by I plus uv. So you multiply both sides by I plus uv, this and this are going to cancel, so you just get u, and then here you will get, okay, so you're going to get I plus uv times u times I plus bu inverse. Now again, see, remember this I plus bu is invertible. So this is the same as you multiply both sides by, on the right, okay, this is on the left, this is on the right, you multiply by I plus bu. Okay, so notice how I'm multiplying on the left once and then I'm multiplying on the right, because that's when the inverses will sort of cancel. So you get here u times I plus bu is the same as I plus uv times u. So notice what happens here. So multiply through, you get u plus uvu. This is if and only if uvu is the same as u plus uvu, and this is true. Okay, so once, see, you start with that equality. If that is true, then it has to happen that the next one is true. If that is true, then the next one is true. Now that is true, then the next one is true. If and only if, these are all if and only if, it can go both ways, right? So once you got finally to this point, it's the same thing. So these two are actually the same equation. Okay, u plus uvu is same as u plus uvu. When you take u out, but keep it on the right here, keep it on the left on the right hand side, and the left on the left hand side, and then you multiply it out, and you get you take the inverse, and on both sides you get the same thing. Okay, so notice how this non-commutativity can be used in some creative ways to get these very neat identities. Otherwise, you'll just get looking at this, you'll be very confused as to why this is to work out. Okay, so there are similar things like this. I'm not going to prove this one. This I will leave as an exercise. So I plus P inverse, assuming I plus P is invertible, is the same as I minus I plus P inverse times P is the same as I minus P of P times I plus P inverse. Okay, so you again use the same method as before. If this is true, then multiplying by I plus P has to be true, and you'll get some very nice trivial equations. Okay, on the other hand, it looks a little non-trivial, doesn't it? Okay. So here is one more that looks even more non-trivial. This u has been gotten rid of here. It says I plus uv inverse is the same as I minus u I plus vu inverse v. Okay, so here you have to be slightly careful here. So first you have to use the problem 2, replace this u times I plus vu inverse with I plus uv inverse u, and then multiply both sides by I plus uv on the left, and you'll get the answer. Okay, so here is again manipulations. I mean, there are a lot of these relationships. This is what I meant by saying when you do multiplication, inverse, all of that together, you get some non-trivial looking identities, or even more complicated ones. I'm not showing you that. Here is a very, very simple one. This is very, very simple. A inverse is the same as A transpose A whole inverse times A transpose. Okay, so notice this. Why does this work? So A transpose A inverse is the same as A inverse times A transpose inverse. So A transpose inverse, A transpose cancels, and you get this. Okay. So why is this interesting? This is interesting because this A transpose A is what's called a symmetric matrix. What is symmetric? If you take A transpose A whole transpose, you will again get A transpose A. It's the same as this. So an inverse of an arbitrary matrix is related to inverse of a symmetric matrix in this fashion. So it's enough if you invert symmetric matrices. You don't need to invert every matrix. In fact, so this is a very powerful idea. So inverting these kind of matrices is easy, and many computing packages will do this. Okay, they take this A transpose A and do something clever with it to find the inverse, and multiply with A transpose to get A inverse. So you'll never find A inverse by elimination. It's kind of elimination, cofactor, all these methods are never used by computers. Computers use different methods, and that's results in importance. Okay. Okay. Anyway, so here is another very interesting thing. Okay. So normally, if you say for numbers A inverse is equal to A, then A square is 1, right? So an A square is 1 if and only if A is plus or minus 1. So there are only two numbers that give you A square equals 1. On the other hand, here is a little challenge. I'm not going to solve it for you, but I'll ask you to do it. You find 2 by 2 matrices A such that A inverse is A. In fact, it turns out there are infinitely many such matrices. Okay, there are infinitely many matrices for which A inverse will be A, and your challenge for you is to try and find these things, and you just have to write it out carefully. In fact, you can even assume upper triangular or lower triangular, maybe not upper triangular. So assume some simple structure. Don't have 4 variables. You can reduce it to like 3 variables, right? You can make 2 of those variables the same, and then try and invert. Even there, you will get infinitely many matrices. Okay. So with that, we'll conclude this lecture. I hope you got some comfort with manipulating inverses, thinking about inverses, and thinking about why algebra and inverses of matrices can be dramatically different from that of numbers. The non-commutativity is one thing, and then the nature of this the object itself is another very interesting thing. Okay, thank you very much.